U-shaped configuration where it goes down in an arc around the maxillary and mandibular arch. So it invades the mesenchyme or mesoderm underneath. This is what we call the dental lamina. Lamina goes down into the mesenchyme, and then at 10 points along the maxilla, and then 10 on the mandible, starts to thicken up right at the bottom. Where it thickens, that's a bud. You get 10 buds top, 10 buds on the bottom. Now the beginning of the deciduous dentition, tooth in the child. And then as it develops, it starts to spread out, forms this cap-like shape. Now you'll start to see what really is the beginning of the enamel-forming structure. This is the enamel organ, part of the cap stage. Yes, really the enamel cells are right at the bottom for the most part. Everything else just part of that formation. Dental lamina still connected to the oral epithelium, ectoderm. And then more development where now the mesenchyme gets dense, very much thicker, pushes up inside the enamel organ, it's now here. And so now this is the papilla. Anytime you hear papilla, that's the mesenchyme or mesoderm. And then right at the bottom, you start to see elongations. That would be Hertwig's. Hertwig's root sheath. You just go with Hertwig's. The beginning of tooth root formation, right down at the bottom. Just what you would expect. Also, you'll hear now the follicle. Just refers to everything all together, the dental follicle. More specifically, you've got the papilla, the enamel organ. So now this is the bell stage, where you get this kind of nice bell-shaped internal appearance. Lamina still attached. And then the fourth stage, advanced or appositional, either way. See the lamina starting to dissolve away, disconnects from the oral epithelium. This is where you hear follicle quite a bit, where it's sort of on its own island of tooth development. And for appositional or advanced, you start to see deposition. Enamel, dentin start to show. So now you're right at the verge of sort of analyzing the cells for tooth development. And then this is all stages of advanced till you have the eruption of the tooth. Bud, cap, bell, advanced. Those are the ones you really need to see. Okay? And then in the actual histology, on your left here, oral epithelium, dental lamina, just lamina, little club shape at the bottom, so the beginning of the bud stage, right there. A little more development, a couple days later, thickens up, late bud stage, even starting to see the papilla, mesenchyme getting dense. And then off to the cap stage, early cap stage here, starts to spread out at the bottom. Enamel organ, all of this. And you'll see a lot of presentations where they're talking different layers and cells, stellate reticulum in the inner and the outer. But really it all comes down to the cells that will ultimately produce the enamel from that little cap. And then the dental papilla, everything else develops from the papilla, the mesenchyme. Bell stage, nice development, arcing inside, Papilla actually pushing up internally. Enamel organ, all for the cells that are going to produce the enamel. And then Hertwig's pushing deeper for the development of the root, either corner there. And then advanced, where now you're seeing layers of deposition right in here. The cells are now depositing what they're supposed to in the development of the tooth. And then we switch to the cytogenesis, the cells. And then singularly, you just get each individually, where you've got the oral epithelium, lamina, bud stage right there. So a nice cap, because it shows how long the lamina can be. Oral epithelium in the stomodium, dental lamina, cap stage. Not unusual to see some intramembranous bone formation as well, starting to develop. That's all mesenchyme, mesoderm. Enamel organ, because all of sort of the dark edge, all part of producing the cells to make enamel. And then late cap, where it really spreads out, nice dark development, enamel organ, and then really see the dental papilla, and even everything around giving you this follicle. All the development going on here. See how elongated the lamina can be, all the way up from that oral epithelium. And even the lamina for the secondary dentition starts to develop as well. But then it'll arrest, it'll stop. Years later, it'll start again. Little intramembranous bone formation. And then think of the papilla pushing deeper, getting more of an arc inside, early Bell stage, papilla, enamel organ, this, lamina still attached, oral epithelium, ectoderm. And then you can see how peaked it can get for the Bell stage. You get a really deep push for the papilla. This would be late Bell. Still don't see layers yet. And then yet the lamina starting to dissolve away, late Bell stage, disconnecting the follicle. Dental papilla or mesenchyme deeply inside the enamel organ. Sometimes you'll hear Ahern's, the little peak. Ahern's knot. Sort of interesting designation for the top of it. Don't worry about that. And then Hertwig's right at the bottom where the root of the tooth is going to develop. Here, Hertwig's, Hertwig's. And then last, now you'll see deposition. This is dentin. Enamel is actually somewhat dissolved away. But now the cells that you've been looking for, their development is starting to deposit their layers. So that makes it advanced. Papilla, quite obvious inside, pulp chamber, dentin forming cells on the edge, everything now getting advanced. And then Hertwig's just pushing deeper in. Development of the root of the tooth. Alveolar bone now well developed. Okay, and then that's just further development, later advanced, showing layers of deposition. So now we're ready to shift from tissues. So now we go from the tissue layers, stages of the bud, cap, bell, and advanced. And then in the advanced, you really see the individual cell layers. So this is external enamel organ, now shows ameloblast, like tall columnar cells, very distinctive. But in a single layer, and that they started right up against these cells, odontoblasts. and then they start moving in opposite directions. So it's like a gunfight or a duel. They actually need to be touching for them to be triggered to deposit their layers. Reciprocal induction, strange kind of necessity for them to be in contact to start the deposition process. And off they go, ameloblast going to the exterior, now laying down enamel, the dark red line. And then in the pulp chamber, in here, odontoblast right on the edge, now laying down dentin. More calcified right there and less calcified next to the cells. Calcification process that goes on in here takes time. So now you've got the layers of deposition for odontoblasts on the inside, ameloblasts on the outside. Enamel from the ameloblast, dentin from the odontoblast. Okay? And then we could further isolate on the ameloblasts, have a rather odd shape to them. There's a body and a tail where they're all interdigitated together. So you get this kind of keyhole look, which gives you the look of the crystal that they ultimately deposit in their march to the exterior. So they do wave back and forth. They don't march in a straight line, sort of a snake-like movement, and yet in the process getting as much contact as possible between the cells, which gives as much contact as possible between the crystals once it's fully deposited. So you hear this enamel rod, which is a body and a tail. When you see the result of what's deposited, the look of enamel crystalline. Now here's an enamel prism or unit where you see as much contact as possible from one crystal to the next. So nature's engineering, trying to get as much strength from one prism to the next. Strongest tissue, densest tissue known to animal tissues. So that's your enamel crystal or prism. It's got that keyhole shape to it. All for strength, for density. And then when it's all said and done, 96, 98% inorganic for enamel. Virtually all inorganic material. Nothing living left when it's all said and done. Say a one-shot deal. Ameloblasts are lost, and that's the end of enamel genesis or production of any more enamel in the tooth. Okay, then we go to the other cells on the other side, into the pulp chamber where we always see the cell bodies of the odontoblasts. They started right here back to back at the DEJ, dentino-enamel junction. Often you'll see little processes there that gives a little hypomineralized result right in that contact area. And then off they go, marching inward, depositing the dentin and the pre-dentin. The only difference is the amount of calcification. We say old dentin and new dentin, or dentinoid. And that these projections, odontoblastic processes, stay in the little tunnels as living components of the tissue, and now involved in calcification. Slow, steady process of depositing the calcium hydroxyapatite, these crystals. And so when you look at them together, here's the enamel, virtually solid, inorganic bricks of enamel or prisms. The DEJ, sort of a scalloped edge because they're not exactly aligned, so you get a little curvature in there. But what you'll hear about are the spindles and tufts, which are really little cell processes. It's sort of make this a little less calcified, just at the base of the enamel. And then the odontoblastic processes, quite elongated, inside the odontoblastic tubules, the dentinal tubules. The living now extended all the way through the dentin, and now the cell bodies at the edge of the pulp chamber, deep within. See how they can get quite elongated as the dentin develops to the interior. And so the look of dentin, all the tubules that you'll see, some you can actually see little odontoblastic processes, clutter inside the tubules. And then when you really magnify, you get a real good sense of the odontoblastic processes inside dentinal tubules. So a lot of them still show those processes separated from the cell bodies in the pulp chamber. Also, a lot of organic material in the crystallization. Enamel calcified at 96, 98%. Dentin, 70% average. Far less. And now a lot of organic component to it, which actually gives it more of a spongy capability versus enamel. It has really no give to it at all. Whereas definitely you have a little give to the dentin due to the organic composition. Favorite technique is to say, well, dissolve all the crystalline structure and leave the organic. You can do it with vinegar. And what's left, odontoblastic processes in the tubules, quite obvious, and then mostly collagen fibers, which is obviously an organic component of the dentin. It's a considerable amount of organic material, whereas if you do this with enamel, nothing's left. It just dissolves to nothing. And then acetic acid or vinegar that we use to do this little procedure to dissolve the crystalline matrix. And so we have, in the complete ground section, where we just use light shining through the tooth, striated appearance of dentin with the dentinal tubules over here. And then you have the initial alignment of the ameloblast and the odontoblast giving you the spindles and tufts. And all I need you to see there is that's just a little less mineralized along that line. A carious pathway if it gets this deep within the tooth. And then enamel, let's say, no real striation to it. Lamella right there, which is actually excess deposition, not really a crack or a defect, which it was once thought to be. And then even light and dark areas, which is just an optical effect, really not structural at all. Right? And then this is where you see the growth lines, get it just right, and you can see these lines at an angle to the DEJ. The main thing with the lines of Retzius or the stripes of Retzius, you're seeing the growth lines of the enamel as the ameloblast march to the exterior, and that they're always at an angle to the DEJ, not perpendicular. So these wave back and forth in their march to the exterior, like growth lines in a tree. And then the DEJ, that line right there, the dentin underneath of that tubular look, or striated look. And then I'd like you to see the entire, we'll say the entire enamel layer here, where we've got very dense, very dark, and then even darker areas which originally they said look like cracks. Craze lines is something I've heard over the years. Well, these are not craze lines. Histologically, these are little extra leaves of deposition from the ameloblast. Why it happens is still somewhat of a mystery, but they're just there as enamel lamella. The only point there is that enamel lamella technically are not pathological. It's not like a crack or a defect. Years ago, there were many, just because the way they look, oh, that's a crack in the enamel. It's actually the opposite. Increased deposition for some reason, here, over here. And then down to the DEJ with the spindles and tufts. This is hypomineralized area, slightly, not greatly, but definitely not quite as dense as the enamel exterior to it. Residual remains of the cells, especially odontoblastic processes. And then off you go down into the dentin. And then when we take it for the overall look, we can see enamel, dentin, pulp chamber within. Say, well, where are the lines of Retzius, stripes of Retzius? Here's the DEJ, and now you see those striations running at an angle, or even somewhat parallel, but not perpendicular like those light and dark bands. Hunter Schrager's, they say don't even care that you bother with those at all. It's just you don't confuse them for Retzius this way. You do it over here, you almost see it like it arcs. The lines of Retzius, or on the surface you can feel them. You know, imbrication lines. Well, this is the surface feel for those little lines of Retzius on the surface near away. Technically, the valley between them would be the perikymata. You want to really be technical. Some think the ridges are the perikymata, but that's the imbrication line. The little valley, that's the perikymata. Don't worry about that. It's not really important. And then even over here, you can see which way the lines are running. This way. The Hunter Schrager are always perpendicular. Stay away from those, go with the growth lines, the lines of Retzius. Like those on board exams, the growth lines in the enamel, stripes of Retzius. And then the tubular striated look of dentin, knowing that you've got those odontoblastic processes all through that layer. Odontoblast, right at the edge of the pulp chamber. So then we'll isolate on those. Pulp chamber on your right here, connective tissue, fibroblast, blood vessels, nerves. And then right along the edge, odontoblasts, which on first look seem to be striated. And you'll still hear clinicians talking about the striated layering of the odontoblasts. We're currently now finding a single cell layer, technically, is that they have a spindle shape to them, which creates the illusion that they're layered or striated. That's an illusion relative to the layer of the nuclei at different layers. And then the dentin pre looks lighter than the older dentin farther out. I have no care that you worry about pre versus regular dentin. It just says it's in the process of being calcified. And that's what you're seeing here, where the pulp chamber, odontoblastic layer, and then the calcifying layers of dentin. New looks lighter, and then the older gets darker, just more calcified. Pre versus regular dentin. No big deal. And then a great specimen for odontoblastic layer in the pulp chamber is here. And that you have to sort of imagine these like little rolling pins, spindle shaped. So that even though it looks like it's striated, you really just have one cell the entire thickness. So it's a single cell layer that now is producing the dentin to their exterior. For now, odontoblast, a single cell layer in the pulp chamber. And then we work our way from the dentin here, root of the tooth, showing cementum, just like bone, little extra depositions, almost identical. Years ago, they said, yeah, these are odontoblasts. Well, now they want you to use cementoblasts, cementocytes. And you see those right at the edge, often described as the cellular part, because of all the cementoblasts and ultimately cytes. And then the protective layer for the root of the tooth of the cementum. So you'll see cellular, obvious, and then this becomes acellular. Pretty much lose those cementocytes. We'll say less like bone in the sense that it tends to fill in more. You don't have those little lacunae or pockets as much as you have in bone tissue. But it's similar in terms of the overall physiology. And then into the PDL on the exterior, creating your gomphotic joint or fibrous joint. Okay? And now we have the CEJ up at the cervix of the tooth, cementum coming up the root of the tooth, and at the best is an overlap of the CEJ, cementum to enamel junction. Now we add this to some degree where the possibilities where most fortunately have an overlap, highly protective, the cervix of the tooth, the neck. Some it's just touching, and still pretty protective. And then the worst case would be there's a gap of some sort from cementum to enamel. Not completely together. Now the dentin is exposed. So that's possibly pathological. It's not getting the protection of the CEJ. And then we complete it, starting with the dentin on the root, cementum covering. Cementocytes and blasts will be right where it looks all that little, those dark spots. PDL, mostly known for its neurovasculature, big neurovascular bundles within. Edge of the alveolar socket, you know as the lamina dura, sort of Wolff's law at work, the thickening of the bone for strength, and then the alveolar bone on the exterior. Just the layered structure from the root of the tooth, dentin to alveolar bone. PDL now giving you the fibrous joint or gomphotic connection. Once fully formed, not really intended to move. Synarthrosis. And this just showing at the apical areas you can have transeptal PDL, cementum to cementum, and then get down into the alveolar socket, and now it's between the bone and the cementum. Over the top, transeptal PDL, if you ever hear of that, which for you is most notable in that it's right below the sulcus on either side. Gingival sulcus or enamel space you'll hear. Just read an article, they're talking about the gingival crevice. Have you ever heard that? This is the gingival crevice? Yeah, so I thought immediately you would tend to reject a kind of crude designation for this space. And that's the enamel. Gingival sulcus, I think, over the years is the one that's most used. Area that you're scaling and very concerned about. Even the connection here with the hemidesmosomes, gingiva to cementum, that delicate connection. Don't want to break those hemidesmosomes when you're probing down into the gingival sulcus. All right. And then just for irritation, recently coming across these little balls of cells, technically from Hertwig's, that wind up in the PDL. few and far between, but you get a little cluster every now and then. They want to have you aware of the epinym associated with these little clusters, technically called rests, little cellular balls that are not actually part of the tissue itself, remains of another tissue. So I need you to know the term Malassez. These are the rests of Malassez, or Malassez rests. These are in the PDL as fragments of Hertwig's. As far as I've studied and looked at, no real pathology. It's almost like an irritation, but no big deal as far as anything negative that I've ever seen. Some will say it could form a cyst in the PDL. So that's in search of a problem, trying to find something that will make these, what you could say, more significant Malassez. Okay, and then we see the technique to show the collagen fibers connecting the cementum, PDL, alveolar bone, lamina dura. It's actually best to see what you've heard about before, where the ligament actually interdigitates into the bone. Sharpie's fibers, all right, gives a very tight connection for the ligament. So you can say, yeah, this is Sharpie's in the alveolar bone. Great preparation for that. PDL, cementum. You even see your cementocytes, the little dots along the line there, the cellular layer. Okay? And then a slide just to show how neurovascular the PDL is. Here's your alveolar bone, dentin, cementum layer over here, and then you've got PDL with these great trunks as far as nervous, and then these are blood vessels. PDL noted a lot for its neurovasculature. Branches of trigeminal all through here. GSA, tooth sensory. It's a great preparation to show how much neurovasculature runs through the PDL. And then your prime area of interest, CEJ with cementum joining the enamel, enamel sulcus or enamel space, sort of an old name right in there. And notice how the epithelium down into the sulcus attaching right at the base. Desmosomes right in there, connecting what is cellular to non-cellular. Cementum. And then I like you to see how interdigitated the lamina propria, which is just connective tissue, is with the epithelium. So over the years, many have been sort of interested in how tight this is, highly protected with the gingiva, where these are anchored very tightly into the lamina propria. So much so, in a healthy individual, there should be a little dimple, a little depression, which is the tug on this. Hear them as reap ridges, deep penetration. Infection sort of softens it up, and now you lose the little dimple. It's not as anchored. So stippling is a good look for gingiva. Shows that this connection is quite healthy. Nice tight connection. Weakened with infection, and now the stippling is not there or not as obvious. That's all due to that nice interconnectedness. How deep they are now intertwined as far as linking the lamina dura with the epithelium. How deep it goes. All for strength, good, healthy contact between the two. Okay, so that says we are done with all the tissues and cells. Now you can just sit back